Hey everybody, welcome to the fourth video of our calculus series where we will be covering both AB and BC only topics. Today we'll be discussing limits with infinity. If you want a more in-depth look at what a limit is and how to approach basic limits, please check out our Introduction to Limits video before watching this one. Limits are used to help us understand the behavior of a function at a certain input value. Now say that we're curious about what happens to a function as the numbers it operates on, or the inputs, get bigger and bigger, eventually getting infinitely large. That's where the idea of limits going towards infinity comes into play. So, our first example, let's say you have a function like f of x is equal to 1 over x. Now what would happen if we started plugging in larger and larger numbers for x? What would be the result of the function? So let's check this out. When x is equal to 1, f of 1 would be equal to 1 over 1. So just 1. Now if x is equal to 10, we'd have 1 over 10, which is equal to 0.1. Now if x is equal to 100, we'd have 1 over 100, which is equal to 0.01. And this pattern would continue. As we keep putting in a larger value for x, the result of our function is getting smaller and smaller. It seems like the function is getting closer and closer to 0 as x is getting larger and larger. As we know, the concept of limit is used to find what the function approaches as the inputs get closer and closer to a certain value, in this case, infinity. So in our example, as the inputs get larger and larger, aka getting closer to infinity, the function is approaching 0. So we would say that the limit as x goes to infinity for the function f of x, where f of x is equal to 1 over x, is 0. This means that as x becomes larger and larger, which is approaching infinity, the value of f of x gets smaller and smaller, getting closer to 0. The function will never actually reach 0, but it gets extremely close to it as our inputs get larger. We may also have limits that approach negative infinity, for which we can use the same principle. Imagine that we have a function like g of x, where g of x is equal to x over 1. In this case, we want to plug in numbers getting smaller and smaller, getting closer to negative infinity. So we'll start off where x is equal to negative 1. In this case, g of x will equal negative 1 over 1, which is equal to negative 1. Now if we plug in negative 10, g of x will equal negative 10 over 1, equal to negative 10. And now if we plug in negative 100, g of x will equal negative 100 over 1, which is equal to negative 100. And if we keep going on and on till the point where we get to x is equal to negative 1 million, g of x will equal negative 1 million over 1, which is, of course, equal to negative 1 million. So you can start to see the pattern that arises, and that as these x values are approaching negative infinity, the result of the function is negative numbers with larger magnitude, and is similarly approaching negative infinity itself. So we would say that the limit as x goes to negative infinity for the function g of x, where g of x is equal to x over 1, is negative infinity. Now you can technically also put that it does not exist because negative infinity or infinity isn't really a value, but a lot of times your teacher will ask that you find if it's going towards negative infinity or infinity and put that as your answer. So far we have solved these limits by plugging in values. And it's not that we can't do this, but this isn't not the very efficient way we could. To solve limits approaching infinity, we just really have to understand the nature of a function as its inputs become very large or very small. So for instance, if we take the limit as x approaches infinity for 2x squared plus 5x, we first want to understand how this function behaves with larger inputs. So if we just look at 2x squared plus 5x, we can already tell that it's a function that will grow and will get larger with larger inputs. Indeed, larger inputs would result in larger outputs, and this function will grow with no boundary. We're always adding, we're always multiplying, we're always getting larger. Since this function allows for that constant growth, as inputs get larger and larger approaching infinity, the outputs would also get larger and larger, and in its own way would also approach infinity. So we would say that the limit as x approaches infinity for 2x squared plus 5x equals infinity. Now moving on to our last example, if we have a rational function. Now if we're to have a limit as x approaches infinity for 3x squared plus 5x over 2x cubed minus 7x. Now this may look very complicated at first, but we just want to approach this limit by understanding the behavior of the separate numerator and denominator functions in relation to each other. And when we have a limit approaching infinity, we tend to only really care about the highest degree term in the function because that'll dictate the behavior. And this is really because when we have such large inputs, a difference in degree will result in a great difference and tends to be the dictator of what the function will actually behave like. So we'll find our highest degree terms in the numerator and denominator. In the numerator, that term will be 3x squared, and in the denominator, that term will be 2x cubed. Now we want to compare these two terms, and the first comparison we want to make is that the 2x cubed term is of a higher degree than the 3x squared term. This means that as our inputs get larger and larger, the 2x cubed term will also be much larger than our 3x squared term. And we'll see this because of that degree difference between the two. And this will mean that our denominator function is going to be growing much faster and will be much larger than the numerator function as our inputs are getting larger, approaching infinity. And like we saw with our 1 over x function, when that denominator is getting much larger than our numerator, the function itself is getting smaller and smaller, approaching 0. And that is the same thing that applies for this rational function. Since our denominator is growing much faster than our numerator, the function will get smaller and smaller, and it will be approaching 0. So we will see that the limit as x approaches infinity for the function 3x squared plus 5 divided by 2x cubed minus 7 is equal to 0. So that's all I'm going to go over today. There are still a lot of things that come with the limits to infinity that I'll cover in future videos. And just to recap, limits going towards infinity are essential in our understanding of how functions behave on a larger scale. They really help us make sense of what happens to functions when the numbers that it operates on are becoming very big or very small. I hope this video was helpful, and make sure to comment down below any video requests you have. Be sure to check out the rest of our STEM content and subscribe to keep up with the rest of our calculus series.